Hello everyone, hello professor. Today my project is going to be about heat losses of the body. Let's move directly to the introduction due to time constraints. So from the early beginnings, people have always understood that something flows from hot objects to the cold ones, and this is called flow heat, right? Heat actually flows from the bloodstream of the body to the air around it. Totally isolated objects or isothermal ones are the only entities free of heat flow, which means you have to be dead in order not to conduct heat. The heat flows that result from the cooling of the sun are the primary processes experienced by humans. On the other hand, the conductive of cooling Earth center and the radiative cooling of the stars are of secondary importance to human life. Usually, we tend to confuse two terms, thermodynamics and heat transfer. We actually studied both of those, and we tend to confuse them. Thermodynamics deals with how heat is transferred, how much work is done, and the final state of the system. However, heat transfer deals more with how heat is transferred with all its modes and at what rate. In addition, it gives the temperature distribution inside the body. So, the human body loses 60% of its heat through radiation, and as a matter of fact, there are heat losses through air conduction and convection too. Heat can be lost from the body by the evaporation of sweat and by forms of dry heat loss. And what do we mean by heat loss is radiation, convection, and conduction. Right? Now we're going to talk about the heat balance. So the total heat of a human body is indicated by its temperature, as we saw in class, and balancing the heat energy flow from the human body comes with an equation that should be respected. M plus R is equal to C plus lambda plus G plus S. So let's talk about those for a second. M is going to be the metabolic rate. R is the power absorbed in the form of radiation. It should be equal to the power lost by convection, which is going to be C. Lambda is going to be the power lost through the evaporation of sweat. G, the power lost through conduction. And S, the power stored, which is negligible in a steady state, which we're going to assume in my project. The heat balance, as we saw, is going to be heat production, heat loss. Heat loss, we already talked about it. Heat production is going to be through exercising, shivering, and metabolic heat production. This picture actually summarizes all of my project, how heat is lost and gained. Heat loss, heat gain can be through the sun radiation, as we saw, the evaporation due to exercise and muscular activity. We're going to have the radiation, respiration, which is related to the basal, quantity, external sources like the sun, as we saw, the conversion of food to heat. Food is going to be the external forces. Now we're going to talk about the rate of temperature change, which is directly correlated to the rate of heat. So as we saw through that one, we're going to see that through that equation, we're going to have the delta Q total over delta T, which is the change of the heat, is going to be equal to a constant C times the change of temperature within the time. The Q dot net is going to be equal to the Q basal, or the change of Q basal over delta T, and the change of Q external with respect to the time. What do we mean by basal is everything natural that is occurring in our body, like sleep and whatever is related to that one, the thinking, everything. If we assume no heat loss, and after a lot of calculation that are actually stated in my report, we're getting into C times delta T over with respect to the time is going to be equal to another constant times P0, which is the basal difference. And therefore, as we can see, the change of temperature with respect to time is going to be equal to a positive constant greater than 1 times the basal change with respect to time, which is literally impossible, as therefore the temperature of our body is going to be increasing at a linear rate, and therefore is going to lead to our death. And within that, we can conclude that the heat losses are necessary to our body. Let's move to the heat loss due to the radiation. Again, here we're going to talk about the heat generated from within the body is given off to the surrounding atmosphere. So as we're gaining heat from the sun, we're radiating through the surrounding. So it's going to be throughout that equation, RL is going to be equal to the surface area of the body times the emissivity of the skin, which is around 98%. Again, the Stefan Boltzmann constant, the absolute skin temperature to the power of 4 minus the environmental temperature to the power of 4. We're going to have to say here that we're talking about the temperature of the skin, meaning we're not considering the clothing part, which is going to complicate our equation much more. And because if we really want to calculate the heat loss due to radiation, we're going to have to calculate it for every part of the body, as every part would have a different temperature. Thus, we're going to have to use a lot of RLs and then combine the both into one. Here, we're looking into the radiation emitted by different objects, within them 2 humans, in a specific place. Here, the infrared camera shows the emitting objects lighter than the other ones, and the reasonable conclusion would be that the temperature of the body of those 2 persons is actually higher than the one of the environment, which explains the radiation emitted by the 2 bodies. Another contrary example, the radiation emitted by different objects in different environment, and this one is actually in Baghdad. And we can conclude here that obviously the temperature of the environment is actually higher than the temperature of the body, meaning, considering the clothes and everything, meaning that the lighting is going to be darker for the body. Let's move here to the heat loss due to the convection. The convection is the process of air or water flowing by the skin and carrying away the body heat, and it is a transfer of energy by means of the motion of the heat transfer medium. In this case, it is mostly the air surrounding it. As we can see throughout that equation, the K convection is going to be actually related to the speed of air, and here is a very interesting application to that one, is why do we feel colder in windy places, even if the temperature is actually higher than in some other places in which it's not windy? Well, here is the answer, as when the speed is actually higher, the Kc is actually higher too, and therefore the heat loss due to the convection is therefore actually higher, and thus we're gonna feel colder. Our body will feel colder. The heat loss due to the conduction, the human body conducts heat to whatever the skin is in direct contact with, and this can be described in that equation as the change in the heat loss due to the conduction with respect to time is going to be equal to the K conductions times the surface body area over the thickness times the temperature of the skin minus the temperature of the environment. And here, as I saw in the literature, they combine the thickness and the K conduction into one variable I, which they approximated as being 0.44 in comfortable environment. In hot environment is going to be 0.1, in cold environment 1.0, and in Arctic environment 10.0. And it actually makes sense, as when L is getting higher, the heat loss due to conduction is getting is decreasing. The human body loses about 2% of its heat through conduction, but I want to mention that it's actually really relevant, as it actually depends on a lot of factors, and the really interesting application of that one, in which the heat conduction is going to be the heat loss conduction is going to be actually much higher, is the misbehaving prisoners in the famous Alcatraz prison, because those prisoners were stripped of their clothes and thrown into the hole, which is an enclosed prison without windows, without walls, and made of concrete, and it has relatively high thermal conductivity. And the prisoners who had to stay there for several days or months had eventually to lay down on the floor, and their large surface area, which is explained by the equation that we had there, made them lose much more heat and therefore felt much colder. Here's an example in which we're going to have the differences between resting and exercising. As when you're resting, your heat loss per time unit is going to be mostly due to the radiation, as in exercising is going to be 80% just due to the evaporation because we're sweating a lot. Danger of extreme condition. I really wanted to talk about that topic because in the literature I found that more than 1,000 people are dying every year in the US from heat stroke because of especially that equation, and the temperature of our body is actually way less than the temperature of the environment, which is going to make this term, which is supposed to be negative, into a positive one, and therefore the heat loss is going to be way higher, which is going to just the heat loss expected by sweating is going to be pretty low. Let's talk about the graph summary. We're having the heat loss from human body in different environmental temperatures. As at very low temperature, less than 5 degrees C, the dry heat loss becomes larger than the heat produced by the metabolism, and the body core begins to cool down, and the hypothermia that I stated in my report sets in, which is a very, very dangerous disease. At a room temperature of 20 degrees C and below, the body maintains its core temperature by increasing its metabolic rate, which actually makes sense. Hyperthermia sets in at an environmental temperature of 37 degrees Celsius and above, because the maximum rate of sweat evaporation is reached and it is not enough to cool the body, which actually shows in the blue graph when it's actually constant in a specific heat energy. If the temperature of the room rises to 35 degrees Celsius, heat loss occurs only through the evaporation of sweat, which actually shows in the blue graph when it is increasing. Again, for a person sitting in a room temperature of 37 degrees C, the dry heat loss in the body is mostly zero. Heat begins to enter the body causing heat death, and that can be shown when the heat is actually below the x-axis, which is the temperature of the environment, which is shown through the dry heat loss. Finally, the room temperature starts to fall, then the amount of dry heat loss begins to increase, which actually makes sense. As a conclusion, the human body loses heat at a constant rate, and this can affect this is necessarily to the body, but again, the heat loss in cold, wet weather increases the risk for hypothermia and cold injury, and this dangerous disease can happen due to swimming or sitting in cool or cold places, because this can cause the body to lose heat very fast, and it is not good for our immunity system. It is very important to be aware of such disease, because it can happen very quickly or gradually depending on the person's age, overall health, and environmental conditions. The symptoms are known. Not a lot of people know about hypothermia, and I hope you guys can read my report and learn about the symptoms, because this already happened many times and a lot of people are dying from it. So be safe, and I hope that you like my project. Thank you.